Alright, back to what I'm saying. So, what do these properties satisfy, right? And again, we're looking at Rn without the concept of distance. This is kind of what we're doing, right? You could say that, oh, it doesn't care about applications, math doesn't care about applications, just because any mathematical property or definition extends itself from the real world, which we define as Rn. This room is R3, right? So you can't really say that. Math has always been kind of embedded in science in some way or another and stuff. Of course, you can be more abstract to science, but we still want to kind of use it or look at it and stuff. It might not even be usable. It might just be for the sake of math and stuff. But why we care is because it kind of looks similar to real life. So that's it. It's generalizing a mathematical space. So it has these properties, right? And first of all, a topology is viewed as a function on a set, right? So, and it's denoted by calligraphic x, right? So it takes this set x and then transforms it into a new set of, but it's still based on x, right? So a topology on x, right, is kind of changes the set, but the new set generated by it must satisfy these following properties. It must contain the set x and the empty set. The empty set reasoning is, the empty set, again, well not again, but is the set of nothing. Okay, why do we care? Because this is how we also generate natural numbers by the piano axioms. So, we care about this, right, and we actually have an axiom of it. It says that the empty set axiom exists and stuff, and most sets usually have the empty set or the set of nothing. I mean, it kind of seems obvious and stuff, but we have to kind of keep it to maintain the consistency of math, and also use it for various other theorems. Right? 2 and 3, the second and third one, is where it gets a little funky, right? It gets more math terms and stuff. So I'm going to just give you the definition and then explain the definitions, right? So it says that for any u, right, in the topology, and any tu in the topology, the intersection for every u in that topology and every tu in that topology, the intersections of those must be in that topology. And thirdly, this is definitely where it gets more abstract and stuff, because this is finite, right? This doesn't really care. It could be finite or infinite. What do I mean by that? I'll explain later. So any subset of this topology, right, for any subcollection or subset of that topology, and we'll say each element of that subset. And if you don't know what this is, you shouldn't be here. So this, we'll just denote it by B1, B2, B2, and so on, whatever. Arbitrary amount of elements in this. So it doesn't really matter how much elements there are. So the union, the union actually of each element in that subset must also be in the topology. Right. So first of all, this is saying for any finite amount of sets, the intersection of two elements in that topology must also be in the topology. And this is saying for every element in the union of all elements basically in that topology is also going to be in that topology. So, yeah. So, of course, this is still a lot. Okay? So I'm going to explain we already explained 1, so I'm going to explain 1 and 2. So to explain, I mean 2 and 3. To explain 3, it's actually easy. I'm going to explain 2 last. We again look at R2. We look at the Euclidean space, right? We notice that, right, earlier I defined, third thing. If U is a subset of X and U is part of the topology of X, we're going to call that an open set, right? So if there's some object U inside that space, right, and U is a subset or subcollection of that set X, it's going to be called an open set. And we also denote a topological space as this, X, as the set of ordered pairs. Ordered pairs to identify what we're taking the topology of and what the topology will do. And this kind of generates a topological space. Right? So, if we look at R2, right, and how we usually call an open set is basically a disk, right? And it contains a bunch of stuff except the outer edges, right? And if we take a bunch of disks, thirdly, notice how X is also in the topology, right? So R2 is by definition an open set. So if we're taking a topology on R2, R2 would be an open set, right, itself. Right? If we take this union of a bunch of open disks, right? Bam, 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 right? What we basically do is kind of view this whole thing, right, as just one thing, right? So, of course, the outer edges are still open. I mean, they still don't contain the outer edges, the edges. And notice how it kind of becomes like a centipede of, but the skin of the centipede is not in the centipede. There's no skin. It's basically a skinless, infinite centipede, and we act like this goes on forever. So this is an endless centipede, right? And this is still open, right? Because if we kind of, and you can continue, right? You can continue this. Add more circles, right? Go up, down, and stuff. Add infinite circles, and then that basically creates R2, right? Because R2 is just everything until it goes to infinity, right? So, because you know how we define an open interval, right? When we have an interval, we have 2, infinity, and this must always be excluded because infinity is not reachable, right? It's not really contained in that interval, so it kind of approaches it. So that is how you can view that. Or again, we could just look at you know, two open circles and take their union, and that just becomes like a nut. Yeah. I was not thinking of the other nut. I also realized that it's also a walnut or a peanut. So I was thinking of the other nut. So that kind of explains why that makes sense and stuff. So how about the intersection? That kind of seems arbitrary, right? Well, I want you to take these two circles, these two disks, right? Look at these two disks, right? Look at them. And take their intersection, which is basically every piece of that disk, of those two disks, that kind of touch each other, right? And we notice that we have to remove this because this is not contained in this one. And we move this, and then we get clitoris. No, so we get this, right? Which is basically an open ellipse. Notice how it contains everything except the outer edges, which is also open, and it can also be viewed as an open disk and stuff. So that is how it makes sense, right? So now, why does it have to be finite? Well, one reasoning is that we can take an arbitrary intersection, right? So we define this intersection as I equals 1 to infinity, right? Of -1 n to n, right? And we're basically looking at r here, right? This is r. Right? So r is a straight line going infinite ways, right? The real number line, right? So we take an intersection of this, right? Of these open intervals, right? And we notice we get -1, 1 intersected with -1/2, 1/2 intersected with -1/3, 1/3, and this goes on forever and stuff. And for them to intersect, basically, the intersection is going to be equal to 0, right? And 0 is yes. So the intersection of 0, which is a single set, right? And which is basically a point. Point 0, right? And a point is closed. Look at it. It's not closed to you. It's closed by definition. So that is why we cannot always have infinite intersections. There could be, but we can't always. We have to make sure that it must maintain its properties, right? Or even, we don't even have to look at 0. We could look at, sometimes we can generate 1, the number 1, the number 2, and stuff. And these are not, obviously, open. Rather, they are closed. So that brings us to our next point. What is a closed subset? What is closed in topological space? Well, it's easy, actually. A set A is closed if so if we remove A from the set X, right, or the I guess topological space of X, right? Oh no, actually that doesn't make sense. So if we remove remove A from the set X, right, and on any topology on X, right, this is going to be open and stuff, then it's closed. And this makes a lot of sense. Notice how if you removed an open set from a closed set, from a closed set, it's going to be open set from a, closed set. We remove a closed set from an open set, it's going to be open, right? Think of, a disk. Look at this. This is a closed disk. And if we remove a circle from it, we get this. A disk without its boundary, right? So, hence, that is our definition for closed. So, those are the fundamentals of a topological space. Now, of course, there's bases and subbases and subspaces and stuff, but that is the intuition of topological space. The reason I made this video was because late at night I was like, oh, look, it's a calculus video and that's intuitional and it kind of tells me what calculus is, and I was like, oh, I like that a lot, you know. But I've seen a lot of calculus videos that show me intuition, and at this point I don't really need it or care. So I was like, let's go to infinite series and see its intuitive, entertaining, topological video, and I realized that it was dog shit, so I'm making my own. to you, my friends.